Okay, welcome back. I'm Shravan. I'm actually taking the moderation part from Michael for the next two presentation. And our next presenter is Colin Quan. Welcome, Quan. It's really my pleasure to introduce him. Colin is currently the Vice President and one of the key technical experts of HiUV, which is one of the market leader of the encapsulation segment. Colin has been the expert of in number of technical standardization committee of China Photovoltaic Industry Association since 2016. Colin is also familiar with most PV module encapsulants quality, performance, and reliability, durability. He has been responsible for participated several standards on PV module encapsulation during the last 10 years in China. And I personally also got a lot of input from Colin for our market surveys on encapsulations. So welcome, Colin. The floor is yours.
Okay, thank you, Siobhan. Hello, everyone. Can you hear me?
Yes.
Okay. Now you can see my table, right?
Yes.
Okay. Okay. Hello, everyone. It's nice to make this presentation for the people here for this meeting. Yes, today my topic is a different solar encapsulant for any needs from standard to bifacial PV modules. The content of my presentation will be from this 7 part. I think the first part I will give a brief introduction of HIUV, and second one I will describe some PV module encapsulant with the EV and polyolefin. What's the difference between them? The third part we will start from a standard BSF PV modules, PID and snail trails issue. That is a serious problem happened in last 10 years. And the fourth part is we look at a wide EVA for pre-crosslink technology, how to increase PV module power efficiency. And the fifth one, the POE for bifacial for the PERC and PERD or HIT, AGT, and BIPV modules encapsulant solutions. And sixth one, the large size fiber like 162, 182, and 210, and even some big size modules are over 500 watts, their encapsulant requirements. And the seventh one, we'll look at the future new PV encapsulant development directions and some requirements from Perovskite and the BIPV, etc. So let's first look at the first part. I will give a brief introduction of HIUV. HIUV was set up in 2005, and from 2009, we began focus on PV module encapsulant R&D and manufacture. After 10 years development, HIUV have become one of the top 3 encapsulant suppliers in PV industry. HIUV's transparent EVA famous for its strong and stable anti-PID ability since 2012, and until today, still without any snail trail customer complaint around the world. HIUV invented wide EVA with the EB pre-crosslinking technology in 2012, which increased PV module power efficiency from 0.8 to 1.5% and keep high yield lamination without white color overflow. HIUV's wide EVA have become standard PV modules for rear side encapsulant for PERC modules and for most first line PV module manufacturers since 2018. HIUV is a POE product that what we call co-extrusion POE or EPE in industry. That was the earliest successful used in PV industry in 2017. And now became the preferred encapsulant for glass modules for bifacial, especially for PERC and N-type PV modules. HIUV has got more than 100 patents related to encapsulant material in PV industry. So here is the HIUV's key customers. As a PV module encapsulant quality technology innovation leading brand, HIUV's EV and POE have been widely used by following key customers, including, you can see, the Longitude, Trainer, JA, Solar, whatever, a lot of personalized module makers, and also a lot of biggest power plant investors here, like SPI here, and China Datang, and whatever, even Adani from India. Yes, a lot of end users and module makers choose HIUV's products at their choice. Here's the HIUV's factory location and capacity. HIUV, currently we have the 4 factories in China. 3 of them owned by the HIUV itself. Another one is our joint venture with the JA Solar. They located in Shanghai and Jiangsu, Zhanggang, and Changzhou. In fact, by the end of the year, we will set up another factory in Taizhou. And tomorrow will be, next year will be in Yiwu, and Zhanggang will be, Zhanggang will be another 3 factories will come in soon, I think. So currently our capacity is about 20 gigawatts. We are planning to increase to the 40 gigawatts next year. So let's look at the second product, PV modules, encapsulant, UV, or polyolefin. So first of all, let's look at PV modules, encapsulant. We always choose EV or POE. Why we choose this? What's the difference between them? Let's have a detailed look at what the EV is. EV is an ethylene vinyl acid copolymer. It's a molecular formula like here. You can see this part is the ethylene group. This part is the acetate group. The aliphatic group here is the polar molecular. This part is really active. Usually they take some chemical reaction from this part. What is most important reaction for the EV is a crosslinking reaction. Look at their crosslinking process. You can see they have the crosslink of the 2 molecular from this position. This is a cross-linking position. They connect another EVA molecular at this position. You get here. Here is their cross-linking bond from here. So their cross-linking process is just like peroxide. They heat divided, then they take the 1 hydrogen from here and another molecule. They all lost the 1 hydrogen. They connect each other. So that is a cross-linking process. Let's look at the POE. The POE's molecular is really different compared with the EVA. What we call it's a non-polar molecular. What inside here only have the polyethylene, and here you have the chances, a short chance with butene or octylene. It's our 4 carbon chains or 8 carbon chains. So this is a totally non-polar molecular part. So because of its is a non-polar molecular, it's not that active. It's hard to take a chemical reaction. So its property is really stable. So like the polyolefin as a encapsulant material can keep the modules really long life and stable. Let's look at how the POE cross-linking. Here is a two molecular. They generally cross-link each other from this position. Because they have a 3 carbon bonds here, so this hydrogen is easily to be lost. So if we use peroxide to take one hydrogen from here, they will connect each other through this position after cross-linking like this. So as it is a non-polar molecular, it's really hard for the polyolefin to cross-link. So usually when the module maker, they do some cross-linking degree test, they find the polyolefin, they just go through the same laminations conditions. They will got some lower cross-link degree. For example, generally EV you can got about cross-link degree about 85. But polyolefin, you only got maybe 70 or even less. So that because their molecular is not so that active, is a little bit difficult for cross-link. So next, let's look at why we need encapsulant EV or POE to be cross-linked. Why we need cross-link. As we know, before cross-linking, the encapsulant material EV or POE is a thermoplastic type with a line molecular structure like here. After cross-linking, it turned into network molecular structure with a thermosetting property here. So after cross-linking, encapsulant EV and POE is mechanical property, thermal stability, and the solvent resistance, and UV and DH resistance stability, and the long-term durability, etc. They all increase significantly. You can see here, here's the reaction for the cross-link. It cannot go back. You know, after its thermal setting property, it's already became a network structure, cannot be divided easily. So it's after cross-linking, it's all got really nice material for encapsulant for the module cells. Okay. So now let's look at the water resistance ability compare between the EV and the polyolefin K. The EV molecular cross-linked structures like this. So EV has polar groups. Polar groups, the EV's molecular chains structure is relatively loose, even cross-linked. And EV's moisture transmittance is high. You can see here is about 25 grams per square meter per day. We calculate on the 0.5 millimeter thick film, okay? The main reason because of this is moisture transmittance high is because it's a polar molecular in their chains. I think they are also because of this polar chains, polar part. Aliphatic groups are easily to be hydrolyzed. Then these chemical bonds will be broken. So, and this all system is easily to be hydrolyzed, easily to be for the moisture penetrate, okay? So let's look at the polyolefin. The polyolefin, the whole system is a non-polar system. Their cross-link structure like this. So the POE, their cross-link structure is more complex and the moisture transmittance is low. So POE cannot be hydrolyzed because they do not have a polar groups. So let's look at how EVA hydrolyze. EVA hydrolyze from this position. You can see with the heat and during the water exist environment, it will be hydrolyzed to the alcohol and acetic acid. So that is why we need to control the backsheet moisture transparency, because if the too much water come into the module, and it will be hydrolyzed to turn into acetic acid. This material will cause a lot of trouble, you know, like the PID, like the crossing to the cells. And this kind of material also can accelerate of the reaction of the hydrolyze, this acetic acid. So as our encapsulant material supply, we also need to formulate our component of the encapsulant material to control the system exist of this acetic acid. So next part, let's look at some summarize of the comparison of the POE and the EVA. So they look at their advantage or disadvantage and their uses. The first, we all know that we have been mentioned before, okay? This is a non-polar molecular gear for the polyolefin, and for the EVA is a polar molecular from this part. So the advantage for POE, it's very stable without acetic acid decomposition, and it have the excellent water resistance ability and good anti-PID ability and long-term durability. While it's disadvantage, and it's not easy to cross-link compare with EVA, need longer lamination time, and which can lower laminate with sometimes with the lamination problem like bubbles, whatever, they can be lower lamination yield. Okay. And another disadvantage is the cross-linking additives like peroxide, easy to separate up from the polyolefin, especially on some hot weather, hot conditions. So it will be separate very quickly. So that will lead POE cross-link degree decline. So maybe some module makers, they have this kind of experience. If the polyolefin put into the hot weather for about 1-2 months, their cross-link degree will drop, especially for pure POE film. The third disadvantage is the price. You know, price is always sensitive. You know, it's much higher than the EVA. So sometimes it's not easy to buy the polyolefin raw material scale. Let's look at the usage of the POE. It's generally, like today, it's mainly used for PERC bifacial cells on real site encapsulant. Because of the PERC bifacial cells, the real site is really sensitive, is a little bit weak for the anti-PID, so need the polyolefin to give them more protections. And for N-type bifacial cells, it's a front site. Front site is a little bit weak, so need a polyolefin. And other usage like thin film PV cells like CIGS, Perovskite, PV modules, whatever, they use the polyolefin to make it resistance of the water and the moisture. Okay. The fourth part is a standard PV modules with a backsheet. They want to have a long-term durability at a humidity area. For example, on the some PV power station on the top of the water, we can use polyolefin as a encapsulant material to ensure this have a longer operation, longer life cycle. Okay. Now let's move to the EVA. The EVA has strong adhesive ability with mechanical property. So EVA also have wide lamination process window with high yield, very easy to operation. Okay. The cross-linking faster than POE can save a lot of lamination time. Generally, I think the pure POE compared with the EVA, there will be at least a 5 to 6 minutes difference for lamination time. And the EVA's raw material rings cost is much lower than POE and easy to buy. And it can have good anti-PID ability based on good formula. So let's look at the disadvantage. EVA's moisture transmittance is relatively high. EVA hydrolyzation generates acetic acid, which can accelerate the PID and crossing the grid fingers, busbar, and cell. So EVA have a polar group, which is not stable as POE. So that is the disadvantage of EVA. Let's look at their usage. Therefore, PERC bifacial cells front side, because front side is really, the bifacial well, can use EVA for encapsulant, no problem. And for the untitled bifacial rear side, yes, they usually with POE, they use together, combine together for the PERC and type encapsulant material today. For many bigger module makers, they are doing like this. Okay. For standard PV modules with a low moisture, so it is the backsheet or GG structure, and for wide EVA, which can be used on PERC bifacial cells rear side to increase modules anti-PID. This part I will do some more explanation later. Okay, so last year I think a lot of module makers they find this kind of phenomenon. Wide EVA can providing really good anti-PID ability compared with the transparent one. Okay, for PERC bifacial cells on rear side encapsulant. So that is a comparison of the EVA and the POE. So the third part, let's look at the standard BSF PV modules, PID and snail trails issue. Let's look at POD. I think all of our PV industry people familiar with this potentially induced degradation. Okay, this kind of problem happened, I think, very seriously in last 10 years. Is just around this period for BSF PV modules. At that time, we found a lot of requests from the module makers and even some of the power plant to do some research how to avoid the PID issues. We do a lot of investigation. We do a lot of experiment, and we publish about this BSF PV modules PID process and the mechanism in 2012 in China firstly. So it was looking like falling. Okay. So here's the glass part. Here's the backsheet. What inside between them is the EVA and the cells itself. Firstly, because of glass surface easy to participate alkaline salt, what we call the sodium oxide. So the second part, the second step, the EV hydrolyze the generate acid here. Then acid react with the sodium oxide to form the sodium ions. Here can move inside this system. Then they enter positive potential sodium ions move to the cell surface and affect the p-n junction even. So that is the whole processing and the mechanism of the PID issue for the BSF cells. Okay, that is a traditional, very traditional power station. Their PID issue happening. This is all of the This is one PV power station at East China. There occurred serious PID problem in 2013. You look at the one strings of the modules from the high power and step by step, one by one, their job to some lower efficiency, even to the zero. You can see here's the EL pictures of this module. Okay, so this is a really serious problem. Now at the same time, I think Japan also, they are facing same situation. They share some information to us. We have some discussion during the exhibition in Tokyo, and here's the one of their testing institute. What's it called? Name is Chemitox. They are testing department for GET certifications in Japan. Okay, so they do one outside real side experiment. It's really interesting. You can have a look. This module outside the PID test, they select one clear day. Their test period is from 5 a.m. to 5 p.m. So this is the whole period what happened for this day. You can see here, it's a solar radiation from here in the morning at the 9 to 10 o'clock is increased, and the air humidity in the morning is really high, and noon is drop, even it then climb up again. And for the module temperature at the beginning is lower, it means generate electricity is going up around 80. That's really common, right? And the air temperature, they increase to the 20 to 30, then drop in the evening. But what is really strange is this line, you can see here, is a link current. Link current happened at the period around 8 to 9, this period. Link current. So the PID and the modules, the link current increase mostly happened at sunrise period in the morning because the dew on the PV glass surface. You can look at this area. This area is just at the foot of the small mountain. Okay, in the morning, a lot of the water, a lot of the dew will be dropped on the surface of the stay on the surface of the module. That will cause a lot of the linkage. So the linkage will be from this way to the frame, from near from the glass back surface, whatever. It can cause some PID issues later. After this kind of PID issue, the power of the module decline very much. Here's another power station. This is a real case research from NATO. NATO is Japan New Energy and the Technology Development Organization. Okay, it's held by the government. They do some of the new project, new energy research policies and for the technology research issue, okay? So they find one power station after 1.5 years operation, they have a serious power decline, even to reach the only 20% of the initial ones, okay? Here's the EL pictures. So it's very serious here. Now they do some detailed analysis. They find if no PID problem usually means higher quality modules. You can see there is no nitrogen, there is no sodium ions and transmittance between the cells, SPN junction. If the PID, what we call it now, we call it a PIDP, it's easy to be recovered if you take the opposite reserve voltage, it will be recovered. They still have some serious problem, like what I gave the name is the PIDS, PID shunting. It cannot be recovered. You can see their PN junction here already moved, looks moved, right? Looks moved. So this PID shunting can lead to BSF PV module lost the semiconductor property. So look at their PN junction. At their research, they said it's about 15% area of the PN junctions area failed, that will lost the semiconductor property. So that was in their research report mentioned. Let's look at more detailed information from PN junction level. You can see the view before and after PID. This is a top view. Look at this no PID area like this, and PID area, it became smooth. Some looks like something failed it. And this is a cross-section review. You can see some cave field phenomena also happened on this PID area. So that is the PID shunting. It cannot recover. It cannot recover. So let's move to the next PID crossing, what I call it the PIDC, okay? In fact, at that time, they do not separate this very well, like with a name like this. This is what I gave the name today. So as the PIDC, they look like some crossing for the great fingers firstly. You can see you can make the great finger to slim line, make the finger slim, and they have some crossing for the silver lines because step by step, which is we'll call the serious PID problem. It also can look at the sodium acetate field phenomena to cover on the AR layer and to make it smooth when PID happens. This is what PID happened here. To compare with the no PID area. So you can see at that time, Japan already do some really deep research on PID issue for the BSF modules, okay? So why this happened? Why is that period happened so many PID issues? I think we can have a look, go back, have a look. The PV industry always seeking many ways to increase cells and modules efficiency. So they find the reduce the cells anti-reaction coatings refractive index is to increase the cells power efficiency. It sounds great. It looks like an easy, very easy way, but people do not. But people never think about it will cause so many PID problems later. You can see about AR anti-reaction coating, their layers is just for protection for the cells. It's this process what we call it the passivation PCVD. Okay. So let's look at what the different anti-reaction coatings property they compare each other. You can look at if we want the cell efficiency higher, then the refractive index is lower. So that here you can define some lower index to make it high efficiency. Now this color looks dark blue, like here, okay? Then its passivation ability is lower. And then the anti-reaction structure is loose. So here's the SEM image, you can have a look. So even today we can look at the PERK cell, the PERK bifacial cell on the rare side is still find it's difficult to have some really compact anti-reaction layers. So it's also facing some PID problem for rare side of the PERK cell. So let's look at the middle. Yes, let's look at the cell efficiency lower. Cell efficiency lower, you get the structure of the ARC is really compact, but the color looks like blue. But people always prefer dark blue, right? Because it looks really nice. Also can make good money for high efficiency. But in fact, only the light blue, this color is really passivation well. It looks like this. It can be high quality and the durability for a long-term operation. So after this kind of a serious problem, people can understand they can operate they can operate anti-reaction film by 3 layers or 2 layers to promote their product durability, and as well as they do not lose too much efficiency. They can select make the layer from lower refractive index to higher step by step, or 2 layer or 3 layers. Or they can optimize their passivation process and anti-reaction raw materials, so it can got really nice high quality cells. So let's look at how our encapsulant material solve this kind of PID issue at that time. We were asking by a lot of module makers to provide anti-PID EV at that time, but we need to do a lot of experiment to select the right formula. Okay, here's the equipment of our experiment in our company. We find that to improve EV's volume resistance is an effective way, but not the higher the better. Transparent anti-PID EV's volume resistance usually more than 15 times, I think, is enough. Also through our test result, also same like this result, okay? And the ways to reduce EV hydrolyze, control moisture transmittance, and cut off the slow down the sodium ions and other metal ions penetrate through EVA. These are all effective ways should be combined together to optimize EV's formula and improve its anti-PID ability. It's not only related to the volume resistivity. Okay. So after we develop successfully with anti-PID EVA, a lot of module makers they test our material compare with others. Okay. This is J Solar. We test our material by triple the testing time. They can use time almost 300 hours to test. We still can got a really nice result for only job less than 2 point. Okay. For the trainer, they test our EV with the brand A. They do some one sales level test. They covered with some Cooper fields, and to increase to accelerate the PID. We are performing much better than other ones. So this is Jinko. They also test about 300 hours. They got the PMX attenuation only 3.9. Okay, this is one of the other module makers. They all very famous for the PV stations, investors, CEP. They also facing some power stations PID problem. They test our material compared with other two companies. We got really nice result, less than 5% decline. Okay. Here's SPI, what we call the CPI before. Okay, they are China's the biggest investors for PV module power stations. Say they also have a module maker factory in West China. Okay, so they do the test of our material compared with other two ones. So this is our result. No decline, and this is another brand. This is another brand. Okay, almost 20% of the decline comparison. It's also another module maker in Hebei province. They test with a foreign brand with covered with aluminum fill for testing. Okay, this one the job only dropped 20%. But look at this cell. Their AR reaction is 2.15. But what they test through our product is 2.15 and 2.08. This one is very weak for anti-PID from cell level. But we still got passed. So that is the EL pictures of these three testing. Okay. So HIUV's EV have excellent anti-PID ability, even on low ARC refractive index cells. Okay. So let's move to another topic. We just finished the PID issue. Now let's look at snail trails. Okay, let's look at the snail trails issue. This really happened very seriously about this period, 2012 and 2015. The main quality problem of PV power station during that period, what we call we can call it the PV cell grid line crossing, and can be called the snail trails, module snail trail lighting track with you know, these mono ones like lighting track, and with poly usually like snail trails or trails, whatever. So what is the reason for PV module snail trails? Most people and even some research report from some research department institute, they think it's only because of the cracks, cell cracks. Is that true? Or is that all? So what is the true reason and how to avoid it? Okay. In fact, at that period, we do a lot of the site investigation. We were invited by some end user, even some PV plant owners to visit their power station to help them to discover what is the reason, main reason for that. We find that the crossing trails across the cells. It's not related to the crack. You can see here. Here is from top left, this module. This module still has some, but this module looks like this. Okay, from here, like a water flow to the right down way. Okay, a lot of snail trails cross a lot of cells. And look at this small cells, small pictures, small part here. A lot of crossing along the edge of the it's not related to the crack. It's not related to the crack. It's another power station. It's in northwest China. It's another one in October 2014. You still can see the snail trails across the cells very easily, okay, on this power station. You can find almost most of the cells, they have the cell as crossing, okay. You can see the color of the grid already turning to brown color, okay. It's one kind of crossing. So this is another power station in the top roof building. It's in South China. We do some investigation here. You can they appears at the cell edge. Each cell edge, they all have some crossing problem. Also some area crossing. Okay. Even some crossing across the trails very often. So that is another module maker. They do test by themselves, okay, in October 2014. They make a module, they make test a brand, one brand, and compare with HIUV for anti-snail trails ability by one cell modules with ground. On the top is the glass, one piece of glass. On the bottom is they select several pieces of the cells with crack, and they laminate it with a little bit bigger size of the back sheet. That they connect each other. They connect it by itself, not each other. They put it just outside for 25 days. 25 days the sun exposure. The module use brand A's EV appear snail trails and the lighting track like here. Here's a snail trail. Here's for mono. You can see for the lighting track. Okay, but HIUV without any snail trails at all. Here's another customer from South China. They're also facing some module snail trails problems. They sell the module to Japan. They are facing really bad reputation for that kind of products. Okay, from November 2014 to August 2015, they do some test with full-size module on the top of their factories. They use with the crack cells. After 10 months after side sun exposed, they check the modules. Snail trails appears issue. Okay, this HIUV is another brand. This is test result. Okay, they use some EV is really sensitive to snail trails. You can see from edge all the snail trails. Some crack area is really serious like this. Okay, this is a same period use HIUV EV, also crack cell. You can see no snail trails and even cell edge crossing. And here is even they make a module without backsheet on backside. Okay, they still do not find any crossing issue here. So let's look at one of the research report from TUV line from Taiwan. I think they do a really nice research on the snail trails issue. Let's look at how they do their research. They select one of the snail trails module. They take out and then take the EVA out. They can see some brown color with the snail trails will be on the EVA surface. This is the affect area, snail trails area. This is the non-affect area. You can analyze this affect area and non-affect area with the element level. Okay, they can find here have some severe element here. If the non-affected area, they do not have severe here, okay? That's only here. This part a little bit far from here, they do not have severe. This is where the great finger exists. So they do some more detailed test of the, look at the, what is the really it is. They test it, it is the silver carbonate and the silver oxide material here. This material can make them shows like a brown color. Brown color. So mainly it's a silver carbonate here material. So they also check the EVA itself. They do some analysis of by organic compound composition analysis. They find the non-affected area, no snail trails area. With the snail trails area, they do some test comparison. They find it's only small part different here. This is a peak from EVOH. Where is the EVOH polymer come from? Where is it come from? So it's come from the EVA hydrolyzed. So that means these affected areas EVA already hydrolyzed. They hydrolyzed, they have the acid and the EVOH polymer. So here you can see the peak. So at this position, their EVA already changed, okay? So the most important, they do another test is they make the module with the wafer, with the wafer, with the cell, just without the grid lines on that. They laminate it together with some sensitive EVA for the snail trails. They put that in the outside for 5 months outdoor exposure. We will find that only the area with the snail with the gray lines, with the green silver lines can have snail trails. Other places do not have. Here is not green lines, no silver lines. They do not have the snail trails totally, okay? So at all these other phenomena and research report, we can get the conclusion. We think the reason for PV module snail trails is as following. The first is the bad additive and a formula or EVA is the main reason that leads to the snail trails and the lightning tracks. Poor quality control of EVA raw material, or maybe some additives, the quality not so good. Maybe they do not mix the process. It's not so very well, so good. So that will cause the problem. The second one is the silver grade lines plays an important role. And without silver grade, it will not happen. And the crack and high moisture transmittance backsheet can accelerate appearance of snail trails. And the electricity and that is why you can see a lot of snail trails come back together with the crack, because it can accelerate that, but it's not reason. The reason is the EVA itself, okay? So the electricity and voltage of PV module is not reasonable. Even some modules, they do not work. They put into the package, you know, they still have a snail trail. It's one kind of the chemical corrosion, okay? Chemical corrosion. That is the whole reason for snail trails, okay? So I'm a little bit late, okay? Sorry, I will up speed, okay? So let's look at pre-crosslinking wide EVA increase PV module power efficiency. Here is a very nice report, very nice research from Spain, from Valencia University. I think they do some tests about 33 kind of backsheet or EVA to test how they reflect to ability affect the power efficiency of the modules, okay? Their conclusion is that white EVA film in generally is the highest global reflectance. And the backsheet with white EVA and also yield the best angle response. Angle response means what they can reflect widely, and the light can be reflected back to the solar cells, okay? We tested the wide EV is backsheet of the reflective ability. You can see the wide EV always higher than in the most range. And also we they tested the backsheet and the pre-crosslink wide EV. This is material, they looks low mirror reflect. They have a really nice angle response. Their reflect light is separated to very widely. This can be reflected back to the module, okay? So the use of pre-crosslink EV can generate more than 2.5 and 6.5 watts per module. But the wide EV is high efficient EV, but it can still bring a lot of problems like white color overflow and white film winking during the laminations. So it's really hard headache at that period.
Colin,
yeah.
Sorry to disturb you, but you know, you really have to finish in 5 minutes.
Okay. 5 minutes. Okay, I will finish. Sorry.
Thank you.
So we find the EB cross-linking technology which can solve this problem quickly. And for the modules, they have a narrow space, so that will have no chance for wide EVA for increased power efficiency. In fact, it's not, because a lot of the bifacial cells, they have the reflectability on this range. On this range, you can see it's a difference compared with transparent EV and wide EV at the right side. So we do some EQE test. We can comparison that part with the wide EV on the back got 2.1 and to 1% current increase. So this is tested with the series K. So as we first turn into thinner, it will be generating more power. Also, the white colors EV with titanium dioxide, they have some negative phenomena in the system which can increase the passive of the right side of the peroxide. That is the reason why it can increase the module's anti-PID ability for wide EVA. Okay. So next, I think will be described some polyolefin with the EPE structure, which can be much better than pure EVE for lamination yield. And also its anti-PID ability shows better than some pure polyolefin. And we can, a lot of module makers, they test our material during last 2 or 3 years, all get really good feedback. And our co-extrusion structure like this, even some only less than 30% of polyolefin inside can pass through their very strict test for PID. Now the HIT cells is really sensitive to the moisture and adhesive. Their adhesive ability is not so good, so that co-extrusion will be solved the problem than polyolefin K. And for the next 2 slides, I think the larger size, we're still facing some anti-PID problem because of the equipment. They cannot do the consistency or homogeneity of the PECVD level K. And for the future, I think for the Perovskite still need some sensitive to the additives of the modules peroxide. So we need redesigning of the encapsulant material, and also the BIPV. Actually, we have already do some preparation for this. So we have been invent a lot of the new encapsulant to increase the strength of the glass. Okay, so at last, I recommended 2 articles here. I think these 2 articles is really what I like during the last 2 years. They give some description onto the PERC cells peroxide PIDs used another article from this article from Fraunhofer. This is from Unreal. They are doing some electronic chemistry of the linkage current enhance the silicon corrosion problem. So that's all. Sorry, I'm a little late. Okay, thank you.
No, I think that's fine. But really, thank you very much for very detailed and insightful presentation. Probably, I haven't heard anything such an extensive, elaboration about snail trials or PID, which is a really very major issue. But unfortunately, we are running out of the time. Since Colin, there were a couple of questions from the audience raised, but since you are also, you will also be part of our panel discussion, maybe I will recommend these questions to Michael when he is moderating. So really, thank you very much for taking such a nice time and giving this wonderful presentation.
Okay, thank you.